In stats, we're going to be coming across sets of data which we are going to want to be interpreting. These interpretations could be in the form of averages, such as means or medians, but we can also look to quantify the spread of the data, this being either your variance or your standard deviation. It's the mean and standard deviation that we're going to be focusing on first, as they are the two that are then going to be the most recurring throughout stats as a whole module. As you may be aware, to calculate a mean, you'll be doing the sum of all the bits of data and then dividing by how many there are. The symbol that we're going to see for the mean may be this Greek letter mu here, although alternatively you may also see it as whatever the variable letter is, in this case that's x, just with a bar on top of it. The notation for working out that total divided by how many there are is in the capital letter sigma, again a Greek letter, of whatever the variable is, so adding all of the x terms together and divide by n, where n is that number of terms. Then for your standard deviation, which is now the lowercase letter sigma, again just think of it as circle with a line coming across the top to the right, that is, in a slightly more complex formula, the square root of the sum of x squared, that's all the x terms having been squared individually, then added together afterwards, over n, minus what is essentially the mean, then squared afterwards. So in this case you would add up the x's normally, and only after the fact do you apply the square. Now the difference between standard deviation and variance, because both do represent the spread of data, is that the standard deviation is in the same units as the mean. In this case we notice if the mean is come from some variable x, then the standard deviation involves some x squareds, either they've been squared already or they're squared afterwards. These then have to be square rooted to get rid of those squares again to bring us back in terms of just a single x. The variance, which is the same formula just without the square root, would be in terms of that unit squared. So while it would still give across the same information in essence, when in later topics we're going to be combining mean and standard deviation in the same formulas, we're going to want to have the same unit throughout, so there's consistency and they can cancel through and so forth. So if those are your formulas, but how do we apply them? Let's just say we had a set of numbers. Let's say so 1, 1, 2, 3, 3, 4, 5, 5, 6, and 9. To start working out our mean and standard deviation, we're going to need the sum of x, so the sum of all these x terms, the sum of x squared, so the sum of all of these numbers individually squared, and then just how many terms there are in total. Well, to add these all up, that would just get you a total of 39. If we were just to square these all first, that would become 1, 1, 4, 9, 9, 16, 25, 25, 36, and 81. Add all of those together for your sum of x squared, and you'll get 207. And then the number of terms is just 10. So to plug these just into our formulas from above, so the sum of x over n, so the sum of x was your 39, divide that by your n of 10, well that will just leave you with a mean of 3.9. As for your standard deviation, we're probably going to want to write out the whole formula here. So we'll have that 207 divided by your n of 10, then minus the 3.9 squared. This would get you a standard deviation of approximately 2.34. So on average, the average of this data would come out as 3.9, and on average they have a spread of 2.34 relative to each other. But what if we didn't just have this individual list of numbers here? What if instead we'd been given to them in terms of a frequency table? So we've got now x terms can be anything between 1 and 9, but then there are 0 instances of 1, 3 instances of 2, and so forth, as we can see in that table. Well, on the one hand, we could now just write these all out in a list and says, okay, so 2, 2, 2, 3, 3, 3, 3, 3, 4, 4, and so forth, but that could take a little bit of time. what we can do instead is, rather than just having, strictly speaking, the sum of x, we're going to have the sum of fx. So the x term times by the frequency, which will be the same as just doing like 2 add 2 add 2, add 3 add 3, and so forth, right? But before we can get the sum, we would need to know the individual terms. So we just need to say, okay, so 1 times 0, well, that's just going to be 0. 2 times 3, 6. 3 times 5 is 15. 4 times 2 is 8. 5 times 1 is 5. 6 times 2 is 12. 7 times 2 is 14. 8 times 3 is 24. And 9 times 3 is 27. So if we were just to work out the sum of fx, that should get us 111. And if we're also just to get the sum of f on its own, which would be the equivalent of working out how many terms there are, our n, that would get us 21. This would be enough to work out our mean, therefore, but to get the standard deviation, we're also going to need the sum of fx squared. So that's going to be 1 squared times 0, 2 squared times 3, and so forth. If we work that through, you should end up with 0, 12, 45, 32, 25, 72, 98, 192, and 243. So to get the sum of fx squared, therefore, that would be 719. Just another thing, with that, depending on whether or not you've kept this original calculation in your calculator, by which I mean if you've done it all at once, like so 1 times 0, add 2 times 3, add 3 times 5, all in one go in your calculator. If you have done that, which is fine, you can then just go back and add squares to all of the x terms. Or what you can do is, if you just have these individual fx's, you can just times them again by x. So just say, well, 6 times 2 got you 12, and 15 times 3 got you the 45, because again, you'd just be squaring that x, just means you times by x again. But either way, now that we have these numbers, we can now say that the mean is going to be your 111 over 21, which is going to get you approximately 5.3. And as for the standard deviation, we'll be doing our square root of the 719 over 21 minus the 5.3 squared, which should get you approximately 2.5. Okay. Now, in turn, another way that these frequency tables could change is that rather than getting you specific x values, they can instead just give you a class width that we're going to be working between. So here, we still have our frequencies. We have a frequency of 4, 19, and so forth for our class widths of 0 to 9 and 10 to 19. As it happens in this case, this table has already told you what you're to use as the sum of fx and the sum of fx squared. So you wouldn't have to work them out manually for yourself. However, just for the sake of this explanation here, I will talk through what you would have to do without that information, just in case the exam didn't give it to you. So, when you're presented with a class width like this, in order to create this mean to have a sum of x of some kind, what you're going to do is you're going to assume that all of the data within each class width is evenly distributed, or in other words, that on average they would come to the midpoint. In terms of working out your midpoint though, what we're first of all going to have to do is adjust the boundaries of these class widths. This is something that is going to come up again in stats and in other places where we look at tables. But the principle is, if the end of this class width here does not match the beginning of this class width here, right now this will be missing data. You're jumping from 9.0 to 10.0. You've basically saying that you're not going to have any distance that's 9 point some decimal, which of course those are going to be there. So what you have to do first of all is adjust your bounds by 0.5 in either direction. All of these upper bounds, we're actually going to say, will be 0.5 above. So this is actually going up to 9.5, and you'll say that this goes down to 9.5. by adjusting those boundaries like that, you now have those class widths meeting halfway between those numbers, and now you have accounted for every possible decimal in between. We aren't missing values. So to continue this, you'd have 19.5 and 19.5 here, 29.5, 29.5, 39.5, 39.5, 49.5, 49.5, and at the top here, 59.5. The one that's not going to change is the 0 here, because to go down by 0.5 in that case would be -0.5, and you can't have a negative distance. The lowest we're obviously going to go is 0 miles. So from here, if we were to now try to look for the midpoints, and for this you may just want to draw up another column in your table for yourself. The midpoint between 0 and 9.5, rather than 0 and 9, is going to be 4.75. But then, as for the midpoints of any of these other numbers, because these have a difference of 10 rather than 9.5, you just need to go 5 in between them. So in this case, that will be 14.5, and as you can kind of tell from the pattern, we're then just going to go up in tens each time. So 24.5, 34.5, 44.5, and 54.5. Now that you have these midpoints, you can now start timesing by the frequency to have your fx. So 4 times 4.75, 9 times 14.5, and so forth. This is going to get you 19, 275.9, 1004.5, 897, 400.5, and 54.5. As we can see, these numbers can get big quite quickly, especially then their sum, which will come to 2,651.4. Now, as for the sum of the frequency, which they technically haven't given here, if you were just to add up these 6 numbers here, you would get that being 100. Therefore, if we were to now start working out our means and standard deviations, for our mean, let's say we're going to use the value that they did give us in the question. But if we do compare, you can see here all they've done is they've taken what the actual accurate fx is and just rounded it to the nearest whole number. So yes, you would get a slightly different mean if you had done it from scratch, but do just use whatever number they've given you. You don't have to prove this like I've done here. This was just to demonstrate if necessary. But yeah, we will use the 2,651 that they've given us, divide by that 100, that gets you a mean of 26.51. Then, as for your standard deviation, we'll be saying that that is, we use their value of the fx squared, so the 80,434.25 over that 100 minus 26.51 squared. And if you put that in your calculator, you're going to get a value of approximately 10.08, which I've just done to 2 decimal places because that is the number of decimal places that we had for our mean. If you wanted, though, you could round that to 10.1 or so forth. Whatever degree of accuracy you feel is appropriate, assuming the question hasn't specified how many decimal places or significant figures you should be giving your answers to. Now it's at this stage, now that we have frequency tables like this with class width, that we can start looking at how we might want to work out medians from data where it's less clear. In the previous lots of data here, if you wanted the median, all you'd have to do is find the value that's directly in the middle. Here, because there are 10 terms, the median technically is going to be between the 3 and the 4 here, because you've got 5 numbers on this side, 5 numbers on this side, so your median will be halfway here, which would be 3.5. And if you wanted, you could then compare that to the mean of 3.9. Or similarly here, if you needed, you could now start writing all these out and work your way inwards towards the middle. But it's here, with these frequency tables with class widths, that you are most likely to be asked for the median, because this is where we're going to use that method of interpolation. For this, we're going to return to the idea that we're going to assume that the data is averagely spread within each class width. So these 4 are each a quarter of the way between 0 and 9.5, and so forth for each of those widths. Thus, we will be able to say, if we can work out how far into the frequency we need to go to find the median, we'll need to go that fraction into the given class width. What I mean by that is that if here the total of the frequency is 100, there are 100 instances of journeys or so forth, the median would be the 50th. So if we now go through these frequencies here, trying to find which row the 50th term is going to lie in, going from smallest to largest. So here obviously we just have 4. Now by the end of this group, we have had a total of 23, because it's 4, then you had the 19. By the end of this group, we would have had 64, because you then add the 41. Well, the 50th, we've already crossed that now inside of this group. Not only do we know that it is in this group, we know exactly how far into this group. Because we know at the end of the previous one we were currently at term number 23, you need to go another 27 before you reach term 50. Therefore, we will say that this 50th term is 27 out of 41 into this frequency. Compare this then to the class width. The class width here, the difference between the lower bound and the upper bound that we've adjusted is 10. So, assuming that the data is evenly spread, if we're going 27 41sts into, or 41ths, I don't know what we call it, into the frequency, we're going to go that same fraction into the class width. So the fraction times class width, in this case that's 10. This would then give you, obviously, how far into the group it is, but you now want to add that to the start of the group. So it's this distance after the beginning. So add that, in this case, to your 19.5. If you do this, you get a median that is approximately 26.1 miles, okay? Which indeed is lying somewhere in that group. So again, just to reiterate, with interpolation, if we're trying to find the median, find out where in which row of the frequency the median would lie in, how far into that specific frequency do you have to go, times that by the class width that it's next to, and then add that on to the beginning of that class width. If we're okay with that, and we can see therefore how we're using these formulas and tables to construct means and standard deviations, as well as now also getting estimates for the median based on your interpolation. Let's just see how you might get along with an example of your own. This here is just another frequency table, as you can see, and so just simply with this, I would like you to once again work out the mean, the standard deviation, and use interpolation to get an estimate for the median. Think about what we just did with the previous table. What might you have to do here? How is it going to be the same? How might it be slightly different? Pause the video, have a go for yourself, and then press play again when you're ready to compare. So, the first thing we're going to want to identify is how this table is different to the previous one. Here, the class widths do line up with each other. This 150 here is the same as 150 here, and they just get away with this by using inequalities, saying that h explicitly equals 150 here, and it's just greater than here. Because these class widths do line up, we don't have to make any adjustments to our class widths here. We don't have to go 0.5 in either direction. We can keep them as they are. Therefore, as we instead first move on to working out what our midpoints are going to be, we can simply just look between the numbers that are printed. So the midpoint of 140 and 150 would just be 145, and we're just going to go up in tens for most of them, although you should watch out because the last class width here now has a difference of 20, so the midpoint here would be 190 instead. So now, therefore, just get your f times x, so your frequency times your midpoints. In this case, that should get you, respectively, 1,015, 1,550, 2,475, 3,325, and 1,710, which, if you add these up, get you 10,000 and 75. And if we were to also just add up our frequency here, the sum of the frequency should equal 60. So if we were to use these, first of all, just to work out the mean before we move on to the standard deviation, what we can say, therefore, is your mean is simply going to be the 10,075 divided by your 60, which would get you approximately 100. And if we just round to the nearest whole number, 168, if you wanted for some decimals, 167.9, 0.91, whatever, however far you want to go, I didn't specify a resolution of your answer. Now, as for your standard deviation, you would now need to be timesing each of these by the x term again. So you'd end up with 1015 times by 145, 1550 times 155 again, and add all of those up. Simply speaking, just to get the answer straight away, the sum of that fx squared you should have got as 1,702,575. Therefore, if we're to do our standard deviation, we have the square root of that number there, divided by your 60, minus, and because we did have to round this one so significantly, I would suggest actually just keeping the fraction as is. So your 10,075 over 60 squared, plug that into your calculator, and you will get a standard deviation of approximately 13.4, or 13 or whatever degree of accuracy you wish to go to. Now, as for working out an estimate for your median based on interpolation, because the sum of our terms here is 60, halfway is going to be 30. So if we now just go through our frequencies to see where we reach 30, so the first row we just have 7, but by the end of the second we've now had a total of 17. End of the third we've now had a total of 32. Okay, well this is clearly crossed over your median value here of that 30. Specifically, we're going to have had to gone 13 into this to reach that 30. So it'll be 13 out of the total frequency of this row, which is 15, times by the class width. Here, the difference between 160 and 170 is just 10. So 3/15 times 10, then add that on to the start of the class width, which is your 160. And that gets you an estimated median of approximately 168.7, or 169 if you prefer. So we can see here the mean and the median therefore are rather close to each other. So to say 168 or 169 should be fairly reliable as an average. If we're happy with that, let's just move on to look at one further concept associated with this topic, that of coding. So if we had this question here, we're told a company manager is investigating the time taken, T minutes, to complete an aptitude test. The human resources manager produced a table of coded times, X minutes, for a random sample of 30 applicants. And we have our data here, where again they've given us values to use for the sum of Fy and the sum of Fy squared already, so we don't have to work them out from scratch. Now, before we get into like the A, B, and C and so forth, again, just to clarify, when we're saying coded, we're saying that the original data that this company manager would have collected to do with the times taken to complete an aptitude test, to make them easier to work out for a mean or a standard deviation for, they have undergone some kind of function. They've either been like times or divided or had something added or minus from them. We'll get to the specifics of the coding in a second, but what we're saying is all of these times here, these are not the actual times that the people took. These are the results of those times having been manipulated in some consistent way to make it easier to look at in a table. So then use linear interpolation to estimate the median for the coded times. Okay, well, we don't need to add up the frequency this time because we already know that there's a total of 30 applicants. So to get the median, we'll divide that by 2, which means we're looking for the 15th. Well, we can kind of tell already if this is 3 here, then add 15, that makes 18. So your 15th applicant is going to be in this second row here. Specifically, we're going to have to go 12 into the row, 12 out of that 15, and times that by a class width of 5, because like with the other example that you just did, these class widths here, they are continuous, there's no missing data, we don't have to adjust them in any way. You would then add that to the beginning of the class width, which is 5, which in this case means that you get a median of 9 minutes. As for estimating the standard deviation of the coded times, well, as I say, we've already got our sums here, so we don't need to work them out. So we can go straight into saying it's the square root of the 5,675 over that total of 30 minus 355 over 30 squared. Put that in your calculator, and you will get a standard deviation of approximately 7. Now it's here that we are told the exact nature of the coding, that the company manager is told by the human resources manager that he subtracted 15 from each time and then divided by 2 to calculate the coded times. So the original time here in T, so T had 15 subtracted from it, and then it was divided by 2. That's how we got these X coded times here. So if we now wish to uncode this data to try and find out what the actual median and standard deviation would have been. In terms of the median, all we have to do is simply put in the x is 9, so 9 equals t minus 15 over 2, and we'll now just rearrange to find what that t is. So you would times it by 2 to get the 18 equals t minus 15, and therefore the actual time of the actual median would be 33 minutes when you add that 15 back over. So for median and mean, you just rearrange and solve exactly as you would any other algebraic expression that you had to rearrange for. The standard deviation, or indeed the variance, however, because this is a measure of the spread of data, how are the data points proportional to each other? If you were to halve all of your numbers, that would mean that your data is now closer together. If we tripled it, they would be 3 times as far apart. And because they're all changing distance from each other by a common factor, this does change, obviously, the average spread. However, simply adding or minusing a number, that doesn't change how far apart these pieces of data are. That's just shifting them up or down on the x-axis. Therefore, when you are coding standard deviation or variance, you only take into account multiplication or division. You do not take into account adding or minusing, because the adding or minusing won't have affected standard deviation. And in fact, if you did put that in now, the effect that would have is to incorrectly tell you, in this case, that the data was now an extra 15 apart from each other, which they are not. So here, simply, all we have to do is take the standard deviation of 7 and just do the times by 2 to get you a real standard deviation of 14. Don't worry about that minus 15. Now that we have this, we can also just look simply at a further extension of the scenario. So the following year, the company has 25 positions available. The company manager decides not to offer a position to any applicant who takes 35 minutes or more to complete the aptitude test. The company has 60 applications or applicants. So comment on whether or not the company manager's decision will result in the company being able to fill the 25 positions available from these 60, and give a reason for your answer. Well, before, if we were just looking at the coded data, it would look like everyone completes it in less than 35 minutes. However, what we have to remember is that these are coded times, not accurate times. So by looking at the uncoded data here, this is what's going to be more helpful to us. Now we could uncode all of these numbers here and look at the rows and then compare. But first of all, this is not for the same group of applicants. This was the first 30, this is a brand new 60. Yes, we are going to assume that the averages stay the same, but we can't use necessarily these exact numbers. All we can really go on is that, on average, apparently, 50% of the people complete the application test, or the aptitude test, in 33 minutes or less. If this median holds true across the different years, if it truly is an average for any applicant, then what we'll say is that, again, 50% will complete it in under 33 minutes. That is less than the 35. Therefore, 50% of all the applicants at least should be applicable for consideration. 50% of the 60 is 30. So we'd say that 30 applicants are probably going to take less than 30, or less than or equal to 33 minutes. And because 30 is greater than the 25, he should indeed, or the manager should fill those positions. It should also just be made note of that it could be that a question gives you like the original data to start with and has you code them. So it could be that instead of like 0 and 5, the data had already originally been like a range of 15 to 25 to begin with. In which case, if you were then given this description of subtract 15 and divide by 2, you would then turn that into the 0 and 5 for yourself. Same if this had been like 25 and 35 and so forth. Just be aware that you may have to do that as well.